Welcome to part 2 of graphs of functions. Before we get into graphing piecewise functions, I want to cover one other function, a little known function called the greatest integer function. So I'll do that first and then we'll get into piecewise. Okay, so 2.2, part 2, graphs of functions. Graphs of functions, part 2 of 2. Okay, so we went over some parent functions, the power functions, the root functions, absolute value function, and here's one more, the greatest integer function. Greatest integer function. And that one has this notation, sort of this bracket. Let me do a better job. Okay, so like this. Okay, that looks terrible. Okay, let me go slowly here. Okay, it's getting a little better. Okay, let me do this one more time. Okay, so it has this sort of look here. So what this means, it's this here is the answer. When you plug in an x value, you will be taking the greatest integer that is less than greatest integer less than or equal to x. Okay, so what that means, so for example, so what that means is if you have, like, let's do 2. Okay, so if you take the greatest integer of 2, well, of course, that's going to be 2. If you take the greatest integer for 2.1, well, that's still going to be 2. Okay, if you take the greatest integer of 2.2, well, that's still going to be 2. And we can keep on going, 2.3, 2.4, 2.5, it'll still be 2, 2, 2, 2. Even when you get to 2.9, it'll still be 2. Okay? And then what happens is when you get to 3, that's when it will change. Okay? Then it becomes 3. But for 3.1, it will still be 3. So it stays 3 for all the 3 point this, 3 point that. And then when you get to 4, then it jumps to 4. And then 4.1, it's 4. 4.2, it's 4. 4.3. Okay. So that's the greatest integer function. And so what happens is when you graph this, okay, so when you graph this, so we already know that we already know there's 1, there's 2, there's 3, there's 1, there's 2, there's 3. So if it's like 1, it'll be 1, right? And then 1.1, 1.2, 1.3, 1.4, 1.5, 6, 7, 8, they're all 1, right? 1, 1, 1, 1, 1, right? And then, so anything in here is going to be 1. And then when we get to 2, it jumps to 2, right? So then right here, it'll be open at 2. And then 2 up here, and it'll be 2 until we get to 3, because it'll be open there, and it'll jump to 3, and it'll be like that all the way up to 4. Okay. Same thing with 0. 0 will be 0. 0.1 will still be 0. And then over here, it'll be open at 1. Okay. And then same thing with -1. Okay. So -1, it'll be -1. But then -1.1, -1.2, -1.3, still -1 until you get there. And that's open. That's supposed to be open. Okay. So there you go. That is the greatest integer function, and that's what the parent graph looks like. And then all of those shifts that we do would happen to this graph over here, so that if you had this +1, it would take all of these steps. We also call this a step function. It would take all of these steps and shift them all up 1. Okay. If it said -2, then it would take all of these step functions and these steps and shift them down 2. Okay. If you had it like this, where you had x -3, then that would shift all of these 3 to the right. Okay. If it were x +3, then it would shift all of these 3 units to the left. Okay, so all of the shifting still applies. This is just a new function to introduce to you guys. Okay, greatest integer function. Okay, so let's get into piecewise functions and how to graph those. Okay, so let's take a look at this one. We'll start off a little simple just so you get the idea first before we get into more complex graphs. Okay, so suppose that I have this piecewise function. So if you remember, a piecewise function is a function defined by more than one function. Okay, so let's suppose that you have the constant function f of x equals 1, which is just a horizontal line at 1. But you have this if your x is less than or equal to 1. Okay, and then you have this function if x is greater than 1. Okay, so this top one is a horizontal line at 1. This one is a line with a slope of 1. Okay, all right, so let's go ahead and graph this. Okay, so I like to take a look at this here, and this is sort of where one function ends and the next one begins. So that transition happens at x equals 1. So over here at x equals 1, that's where the transition happens. Okay. All right. So let's have a look. This graph is easy to graph. It's a horizontal line at 1. Okay. So this is a horizontal line at 1, but only for the x values that are less than or equal to 1. Okay. So here's 1. And it's a horizontal line, but only for the x values that are less than or equal to 1. Okay. This function, x plus 1, is going to be a line with a positive slope. Okay. And here, this graph will only be for the ones that are greater than 1. So what you can do is figure out, well, 1 and 2. Okay. So when x is 1, I get 2. When x is 2, I get 3. Okay. But this one will be an open point because this is an x value that is not here. That doesn't fall in here. Okay. So 1, 2. open, and then 2, 3, 2, 3, and that can be closed. And this will be the graph for all of the x values that are greater than 1. Okay, so I used this actual point, even though it's not part of this guy's domain. I used it because if I started with 2, if I chose 2 and 3, then I would have missed all of these points here. Okay, so because you would have graphed this one and everything larger. But remember, x values that are greater than 1 include 1.1. So you need to know what's happening with the graph here. Okay, not starting at 2. Greater than 1 doesn't start at 2. Okay, so we have to get all of those points that are very close to 1. So that's why I start with 1. I start at 1, but I know it's going to be an open point. Okay. All right. Let's take a look at another one. Let's go ahead and graph f of x. So we'll have 2x plus 3. We'll have this one if x is less than -1. And then we'll have this graph, 3 minus x, if x is greater than or equal to -1. Okay. So again, here at -1 is where the transition between the two graphs happen. Okay. So right here at -1. Okay. So to the left of the graph, I have 2x plus 3. So I'll do it over on this side, on the left side. So f of x equals 2x plus 3. And what I'll do is I will choose -1 and I'll choose -2. Okay. And then for the right side of -1, right, I will choose, we're going to be using this this function, and I will choose -1 as well, and 0. Okay. Now we see here that for both my graphs, I chose -1, the x value where the transition happens. Okay. But only one of these will be a closed point. The other one will be an open point. Can you tell which one will be the closed point and which one will be the open point? Okay, so right over here, this is strictly less than -1. So this one, 2x plus 3, will have the open point. Okay, and this one will have the closed, because -1 falls in here. Okay, all right, so let's fill in our tables. Let's do this table first. When x is -1, 2 times -1 is -2. -2 plus 3 is 1. Okay. -2. 2 times -2 is -4, plus 3 is -1. Okay. All right, so let's go ahead and plot these. -1, 1, open. -2, -1. And we have that. Okay. The right side, let's fill in this table to get the right side of the graph. When x is -1, double negative becomes positive, so that becomes 4. And this, we get 3. Okay. All right, so -1, 4. 1, 2, 3, 4. Close point. And then 0, 3. Right there. And we will have this graph. Okay. So again, we don't draw the entire graph, okay, because we only have this for the x values that are greater than or equal to -1. So that would be only on the right side of -1. And we have this graph for x values less than -1, which is to the left of -1. Okay, so make sure you don't graph past -1. Make sure you don't graph this one past -1. Okay, -1, base over here, -1 is where the transition happens. That's when one graph stops and the other one begins. Okay. All right, let's take a look at this next one. Let's go ahead and graph this piecewise function. Let's do 1 minus x squared. So this is a parabola reflected over the x-axis and then shifted down 1. And we will have that if x is less than or equal to 2. And then we will have this simple line if x is greater than 2. Okay. All right, so 2 is where the transition happens. Okay. To the right of 2, we will have f of x equals x. On the left of 2, we will have f of x equals 1 minus x squared. Okay. All right, so let's do, this one's a little easier, so let's go ahead and do this one. This is for x values greater than 2. So I'm going to choose 2 and 3. Okay. And this one is going to be open because 2 is not included. Okay. All right. So we get 2 and we get 3. So 2, 2, open, 3, 3, closed. And we have this graph for the right side of 2. All right. The left side of 2 is going to be this parabola. Now, I'm going to use some green here. Okay, so parent function 0, 0, 1, 1, -1, 1. And then it's going to flip. So then -1, 1, -1, -1, 1, -1. Okay, so these 3 are now the parabola. Okay, and that's because this got multiplied by -1. Another way to look at this is like -x squared plus 1. And so now you can see, okay, this is going to multiply the original y values, and this is going to shift it up 1. Okay? So we don't need this, and we don't need that. So now these are all going to shift up 1. So I'll put X marks there, there, and there. Okay? And what happens at 2? We get, looks like we get, when I plug in 2, f of 2, I get 1 minus 2 squared. 1 minus 4, -3. Okay, so then, so here, and this one will be closed. Okay. So this will be closed. Here, let me do it in black, the final one. This will be closed. And then we have our parabola going towards those x's. And then this one can go forever. Okay. But the right side of the parabola does not go on forever, only this side. Because you only have the parabola if for x values that are less than or equal to 2. These are the x values that are less than or equal to 2. So you only have the parabola for these x values. Okay. All right. So that's how you do the piecewise functions. You just really have to make sure that you stop the graphs at this value. One of them will be a closed circle, one will be open circle. Okay. All right. So that's it for piecewise. There's one more thing I need to go over, the vertical line test for functions. You might know this already. So vertical line test for functions. So if you're given a graph and they're asking you, is this a function, yes or no, you can use what's called the vertical line test. Okay. So this states that a curve in the coordinate plane is a graph of a function. So when we say a curve in the coordinate plane, what we're talking about there is just if we have a graph, okay, we call graphs curves. Okay, so a line, we call that a curve. A circle, a parabola, absolute value, all of these. Okay, so a curve in the coordinate plane is a graph of a function. If and only if you don't want to write all of that, you can do this IFF. IFF stands for if and only if. Okay. So if and only if no vertical line intersects the curve more than once. And I'll show you what that means. Okay, so here's a visual of what this is trying to say. All right, so if you have a graph and you're trying to figure out, oh, is this graph a function, yes or no? You can use a vertical line test. Just if you can draw a vertical line anywhere through this graph, it should only intersect the graph once. So drawing it anywhere, if I do this, then it intersects only once there, right? And that's true anywhere for this graph. If I draw a vertical line, it will only cross once. Okay, so this here is a function. However, if we take a look at this graph, okay, suppose that I have this, and now it's sideways. If I do a vertical line, well, it crosses 1, 2, more than one place, okay? So if it crosses more than once, so if it crosses the graph twice, 3 times, 4 times, 5 times, then this is not a function. Okay. All right, so that is it for part 2. If you have any questions, make sure you message me or email me.